All right, so let me remind you that this is somehow the main theorem of my series of lectures. I formulated it last time. So the thing on the left is the co-rank of the Selmer group for the p-power descent. On the right-hand side is the analytic rank of the elliptic curve over Q. And so what I'm going to do today is to somehow present the proof modulo the existence of certain symplectic form, and the remaining two lectures will be somehow devoted to the general theory behind such symplectic forms. Maybe I should give you some references. I don't quite remember them. So there's one paper in Compte Rendu, which appeared in January 2001. It's a very short paper with this proof, except that it uses a certain black box, and the black box is explained in a generality which is maybe incomprehensible in my preprint on Selmer complexes, which can be found on my webpage. All right. So how can I approach such a result? Well, first of all, let me remark that luckily we know that every elliptic curve over Q is modular. So E is modular. Therefore, if you write the L function of E as the Dirichlet series, the sum of an over n to the s, then the corresponding function, the sum of anq to the n, let me call it Fe, is then a cusp form, in fact a new form, on gamma naught of n, where n is the conductor of the elliptic curve. All right, so this is good news. So in fact, this is a theorem about modular forms rather than about elliptic curves. And so among other things, the right-hand side is well defined. After the first observation, the second observation is now this condition about E having good ordinary reduction. So E has good ordinary reduction is equivalent to saying that P does not divide n times AP, where AP is the P's coefficient here. All right. So let me give you an idea of the proof first. So the general idea is the following. In this p-adic world, somehow there is a lot of freedom, and Selmer groups usually don't appear on their own, but they live in families, in p-adic analytic families. So the idea is to embed the Selmer group we are interested in such a family. So the first thing is to embed, so there is some one parameter p-adic family of Selmer groups I don't know, S depending on some parameter lambda, such that for a special value of this lambda, say lambda 0, we recover the Selmer group we are interested in, the Selmer group of E over Q. All right? And these Selmer groups really should be somehow not just any Selmer group, so they should be related to L functions at central point. In the conjecture of Birch's-Swinnerton-Dyer, of course, the analytic rank has something to do with the behavior of the L function at the center of symmetry of the functional equation. And in the same way, we should look only at those families which are always central. So these have some chance to be self-dual. So morally, what's going on is that the quantity on the right-hand side, in other words, the analytic rank modulo 2 can be read off from the functional equation. All right, that's the main, somehow, one of the main ideas. So once we have this family, what can we do with that? Well, we can look at those Selmer groups and see how they vary. Maybe as lambda approaches lambda 0, in other words, locally in the neighborhood of lambda 0, or possibly globally in the whole family. Let's see what happens. So we need three ingredients, in fact. So the first ingredient is to have a suitable Euler system. The second ingredient is to know that the Euler system is non-trivial. So a non-vanishing of the Euler system. And then the third ingredient is a certain higher dimensional version of the Castle's pairing. So what do we do with those ingredients? So whenever we have an Euler system which is non-zero, then we get some statement about either the orders of vanishing of the periodic L functions or about maybe the exact values in terms of the Selmer groups. And so here the statement which you get is that for generic values of lambda, if you look at the corresponding Selmer group, this is again a ZP module of cofinite type. So if you look at its corank, then it's small. It is either 0 or 1. It is for a given family, it's one of those two values. It depends somehow on circumstances. Okay. And this is a usual behavior of what one expects. So if you have a family of L functions, then usually the order of the vanishing should be almost always either 0 or 1. Okay. Now, what is this Castle's pairing good for? This implies that if you look at those coranks, so somehow if you look at the difference of the corank at the special point, lambda naught, minus the corank at a generic point, as lambda, so these are always non-negative integers, as usually in a family where h0 is rigid, and h1 somehow, the dimension of h1 can only go up. It cannot go down at a special point. So if you have such a pairing, then these jumps are even. So this is a consequence of the existence of this pairing. So why are those jumps even? Well, because they are controlled by the torsion in some h2, and as I indicated last time, in good self-dual circumstances, there is a non-degenerate symplectic, there is a symplectic form on such a group, and therefore the corresponding rank or the dimension of such a group is even. All right, so this is how this works. All right. So there is in some sense a relative statement here saying that the jumps are even, and then an absolute statement which identifies the generic coranks, the generic dimensions. These are completely separate. So in the first approach, which was not quite successful a few years ago, so this was done jointly with Andrew Plater, what were the three ingredients? So the idea was to use Hida theory. So what does it mean? So we have this modular form Fe associated to E, and by assumption it is ordinary. And so by Hida theory, this is an element of such a one-dimensional family. So this is an element of a p-adic family, say F lambda of ordinary new forms of varying weight. So to each of them you can associate a certain Galois representation, and to each Galois representation you can associate a suitable Selmer group. Well, you have to make some Tate twist to make the Galois representation self-dual, but you get the correct objects, like here, associated to the central point of the corresponding L function of the form F lambda. All right. So what are the corresponding objects here? So is there an Euler system? The answer is yes. In fact, one has to use two different Euler systems depending on the answer here. In other words, depending on the parity on the sign in the functional equation. So one has to use either Kato's Euler system. This is in the case when the sign is plus. In other words, when 2 divides the analytic rank. And when the analytic rank is odd, when there is a minus sign in the functional equation, one has to use the Euler system of Heegner cycles. So these are some higher dimensional generalizations of Heegner points which have something to do with the behavior of the L functions at the central point, but for forms of higher weight. So these were studied in some of my older papers. Okay, so the Euler system exists, and there are reasonably good results about Selmer groups using these Euler systems. Now the third part also exists. So the symplectic form exists. This will be done in the third and the fourth lecture. But there's a problem with the non-triviality. So this is not known in this case because somehow, in fact, there is a two-dimensional family. So one variable is weight, the other variable is the point at which we are looking. So we will need some non-triviality of these objects restricted to the central line. And this is not known. We only know that generically these things are non-zero, but maybe not when they are restricted to the central line. So this is a problem. So all we can say is that this would follow from a purely analytic statement. This would follow from what's known as a conjecture of Greenberg. Greenberg's conjecture on non-vanishing of what's known as the two-variable periodic L function for a Hida family restricted to the central line. Well, when I say restricted, again, this is not quite to the central line. So what's happening is that there are two variables in this periodic L function. There's the weight and then the usual variable s. So we want to look at the point s equal to k over 2 as usual. And so sometimes if the sign in the functional equation is minus, then the restriction is automatically 0. So you have to divide by the equation of the line. So Greenberg's conjecture tells you that generically the order of the vanishing along this line should be 0 or 1. And so then the results on Euler systems would actually imply what we need. That the Euler system itself restricted to the central line would be non-zero. Unfortunately, this is not known. As Pierre Colomb has mentioned, people doing analytic number theory don't know enough about periodic numbers actually to prove what we need, unfortunately. So this first attempt was unsuccessful. There was only a conditional result saying that Greenberg's conjecture would imply theorem 1. All right. So, but luckily, one can use another family. Second approach, successful, which uses anti-cyclotomic Iwasawa theory. So how does this work? One does not work over Q, but over a suitable imaginary quadratic field. So one works over some k equal to q square root of d, where d is negative. And in fact, the extension k infinity over k, which just appears in earlier lectures, for example, in the lecture by Erikshoven. So this is the anti-cyclotomic, or if you wish, dihedral ZP extension. So this is ZP extension, which is a part of a dihedral extension over Q. So what are the three ingredients in this case? So the Euler system is just the Euler system of Heegner points that we've seen already. The third, now the non-triviality of the Euler system is what was formerly known as Mazur's conjecture, now a theorem of Cornu and Vatzal. Mazur's conjecture. And the third part again is fine. This should be the content of the last two lectures. So what I want to explain in today's lecture is how this approach using anti-cyclotomic Iwasawa theory works, and how it reduces the statement of theorem 1 simply to the construction of a suitable high-dimensional Castle's pairing. So let me begin by some complete trivialities. Again, I apologize to most people in the audience. Let me get back to the elliptic curve, back to E. So E is an elliptic curve of the form y squared equals x cubed plus ax plus b. A and b are some rational numbers. So if you have now any, let's take now any quadratic field, k, q, h1 square root of d. Quadratic field could be real, could be imaginary. Quadratic field, but of discriminant d. D is the discriminant. So then we have the twisted curve ED, which is the curve dy squared equals the same polynomial here, x cubed plus ax plus b. And it's well known that the behavior of E over k is equivalent, somehow arithmetic of E over k is equivalent to the arithmetic of E and ED over q separately. You can say that there are some motivic reasons for that, but let me just list some well-known facts about this. So, for example, if you take the analytic rank of E over k, this is equal to the analytic rank of E over q plus the analytic rank of the twisted curve ED over q. This is simply because the L function of E over k is the product of the L function of E over q times the L function of the twisted curve. And similarly, you have the same additivity, for example, for the corangs of the Selmer group. So SP infinity of E over k is equal to SP infinity of E over q plus SP infinity of ED over q. Why is this to work? For example, these are dimensions of the Bloch-Kato-Selmer groups, which depend only on the Galois representation. So it's just a question of the well-known behavior of the Galois representation. So if you take this representation VPE, this is the representation of the absolute Galois group of Q. If you take the restriction from GQ to GK, and then if you then take the induction from GK to GQ, this is the sum of the original representation plus its twist, plus the corresponding representation for the twisted curve. Now again, those two equalities are in fact manifestations of the same decomposition for the motive H1 of the elliptic curve, all right? And similarly, there's this, so let me denote those two additivity properties by star. I will be referring to them. Now similarly, you have the additivity for the usual ranks, model Weil ranks, although we don't actually need that. Let me add it to the list just for completeness. So you have R of E over k equals R of E over q plus R of ED over q. This is because if you write the Galois group of k over q, this contains, this is generated by the non-trivial element tau. And so if you look at the eigenspaces of the Molde-Weil group, so if you define by, so Ek is almost the sum of its eigenspaces under tau, modulo some two periodic group. So if these are just eigenspaces where tau equals by x by plus or minus 1, then of course Ek plus is simply the group of Q rational points on E, while EK minus is canonically isomorphic to, well, maybe not quite canonically, almost canonically isomorphic to the group of rational points on the twisted curve simply by sending the point xy in here to the point xy divided by the square root of d. You have to choose the square root. Okay. So that's this decomposition. And also, there's a formula for the sign in the functional equation of the L function over k. Well, the formula is nice if the discriminant is relatively prime to the conductor. So the formula is the following. This just tells you that -1 to the analytic rank of E over k is equal to this quadratic character corresponding to the quadratic field k evaluated at -n. Okay. That gives you the sign of the functional equation. So in particular, this also justifies what people have said before, that in the presence of the Heegner condition, the sign is -1. So now let me now state this once again. We say that k satisfies the Heegner condition although I think that in this abstract context this was defined by Birch. So the Heegner condition Heg with respect to the curve E, if the field is imaginary and each prime L dividing the conductor splits in K. So we've seen this condition before, and this of course implies that this root number, the character d of -n, is just the value of this character at -1, which is -1 because d is negative. And therefore, the analytic rank is odd for the curve over k. This also works in the situation considered by Darmon when k was real and there was exactly one inert prime and everything else was split, and you also get the sign -1 because of this formula. All right, so using, well, let us remember this additivity, all right? So using this additivity, one can reduce theorem 1 to a similar statement over k. So let me formulate it now. Theorem 2 is the following. So if E is as before, if E is as in theorem 1, in other words, an elliptic curve over Q with good ordinary reduction at P, and if K satisfies the Heegner condition, then we have the same parity statement over K. So the co-rank of the Selmer group of E over K is congruent to the analytic rank of E over K mod 2, which is of course congruent to 1 mod 2 by the calculation of the root number. This is an analog over K. And so let me now show you why theorem 2 implies theorem 1 quite rapidly. So proof of the implication theorem 2 implies theorem 1. Of course, the idea is that theorem 1 is about the behavior over Q, so one is allowed to vary K in theorem 2, so let's do that. So the first case to consider is when the analytic rank of E over Q is odd. So in this case, this means that if D satisfies the Heegner condition, then the analytic rank of the twisted curve is even. And in this situation, there's a result of Waltz-Bourget, also proved by other people later on, implies that there is an imaginary quadratic field K satisfying the Heegner condition such that the L function of the twisted curve does not vanish. In other words, such that the analytic rank of the twisted curve over Q is 0. Now, if the L function does not vanish over Q, then a theorem of Kolyvagin, of course, it relies on the results of many others, Gross, Zagier, another non-vanishing result by other people. This implies that in this case, the full Selmer group is finite. In other words, the Selmer rank of the twisted curve also 0. And remember, there were those additivity properties relying these quantities over K and over Q, and now using them we just see that everything follows, because now all we have to do is to combine those two additivity properties, which are called star, with theorem 2 gives theorem 1 in this case, because both quantities here are in fact equal to the corresponding quantities over Q, because those two other terms vanish. Right? So this was the case when the analytic rank was odd, and the same well, just a variation of this argument proves theorem 1 in the other case. So if 2 divides the analytic rank of E over Q, we can play the same game, but the beginning is easier, so you choose any quadratic field, imaginary quadratic field satisfying the Heegner condition, and such that P does not divide the discriminant. And in this case, we know that the parity of the twisted curve is quite opposite. Therefore, the twisted curve ED satisfies the assumption here and also satisfies the assumption of theorem 2. So, in other words, this means then case 1 applies to the twisted curve ED, and therefore we get that the Selmer rank of ED over Q is congruent to the analytic rank of ED over Q mod 2. And again, we are done because we combine this with the additivity formula star and theorem 2. So this is how, by varying suitably K, it is in theorem 1 can be deduced from theorem 2. So all we have to do now is to fix K and prove theorem 2. So, well, I think we remember the statement. So let's try to prove that. Proof of theorem 2. So we have this anti-cyclotomic ZP extension. So this is the unique tower of fields. Tower of fields. Q, K equal to K0, K1, K2, etc. K infinity, which is the union of Kn's. Here, Kn, the Galois group of Kn over K is cyclic of order P to the n, and the Galois group of Kn is also Galois over Q, and this is dihedral. So what does this mean? Well, let me just write this down in the limit, which is all we want. Now, where does this really come from? Now, so Darmon wrote in his first lecture that various Hegner points are defined over abelian extensions of K, but these are very special abelian extensions. These are those on which the complex conjugation acts by -1. That's how we get a dihedral extension. So in the limit, we get the following exact sequence. Here we get the Galois group of K infinity over K, which I want to denote by gamma. So this is isomorphic to ZP. Non-canonically, here is the Galois group of K infinity over Q. And here is the Galois group of K over Q as a quotient. Remember, this had two elements, 1 and tau. And this sequence splits. So let me fix a splitting. And so I got an element here, which lifts tau, is also of order 2. So this means that tau square is equal to the identity, and its conjugation action here acts by the inverse. So tau little gamma tau inverse equals gamma inverse for every little gamma in capital gamma. That's what I mean by dihedral. And again, this comes from class field theory, in fact, because these are certain quotients of the Picard groups of those orders, as in the lecture of Erikshoven. And so if you have an ideal times its complex conjugate, and this is a principal ideal generated by its norm. So that's why you get this product is trivial in the corresponding Picard group. Okay, so you get a dihedral group, and this is really important. I mean, this dihedral extension is very special. I think no other ZP extension of K has similar properties. So this is called the anti-cyclotomic extension. So K infinity over K is the anti-cyclotomic ZP extension of K. Yeah. So now, as in the lecture of Erikshoven, in his last lecture, let me fix some modular parametrization of the elliptic curve E, say pi defined over Q, and the Hegner condition, together with the fact that P did not divide N, allows one to define Hegner points. I don't remember the notation, maybe it was xn defined on E over Kn. So remember the way they were defined, there was some modular construction of points on x0 of n. One took their image on E. These were defined over certain ring class fields, which were slightly bigger than Kn. Then I wanted to take trace. So after taking the trace, one obtains some points xn, and Mazur's conjecture stated that for some n, the corresponding Hegner point is not torsion. So this is now a theorem proved by Corny and Watzau. And again Corny, okay. Twice. In fact, there are various versions which are, under my assumptions, equivalent. You can say that there is n, or for all but finitely many n's. These are equivalent under my assumptions. And now the reason why this may be interesting is that whenever you have a ZP extension, then there is, you can apply Iwasawa theory, which allows you to deduce arithmetic over K from what's happening over K infinity. So let me just briefly remind you of how this works in our context. So if you want to do Iwasawa theory, so So first of all, you have to work over the Iwasawa algebra, which is the completed lambda, which is the completed group ring of gamma. In other words, this is the, as usual, the projective limit of the group rings of the Galois groups of finite layers of the extension, Galois groups of Kn over K. This is non-canonically isomorphic to the power series ring in one variable over Zp. And you have to work with some lambda modules. So what kinds of lambda modules do we get? Well, the most interesting one is one which I want to call S infinity, which is you take the Selmer groups of E over all layers Kn, and then you take their inductive limit. So this is a lambda module of cofinite type. What does cofinite type mean? This means that the Pontryagin dual S infinity hat is of finite type. Okay, so this is the basic object one wants to study, and let me just state two facts about this module. Without proof. Right? So, what is the first fact? Now, there is a canonical map from the Selmer group over K, the object we are really interested in, into gamma invariance of this limit. So you have this canonical map, and it is known that this map has finite kernel and co-kernel. So this is a special case of what's known as Mazur's control theorem. So by the way, I mentioned last time that in fact the assumptions in the theorem can be relaxed. So for example, one can prove it for curves with multiplicative reduction and P, but for those curves this is not true. So, but if one uses, for example, those extended Selmer groups, it's still true, and so one can, the proof somehow goes through with slight modification. Okay, so this is finite kernels and co-kernels. In other words, all we have to do is to look at very carefully at gamma invariance in this module S infinity, or if you wish, at gamma co-invariance of the Pontryagin dual, which may be a more accessible module. Now the second fact is the following statement, that if you suppose, if you assume Mazur's conjecture about Heegner points, this tells you something about the rank of, about the co-rank of this module. So the co-rank over lambda of S infinity, well, which by definition is the rank of the Pontryagin dual. This is finitely generated module, so you take its rank. So Mazur's conjecture implies that this co-rank is 1 under our assumptions. So this was essentially proved by Bertolini. Maybe you have to get rid of some assumptions, but he did that. Now, so one should really view this as a somehow lambda analog of Kolyvagin's result, Kolyvagin's theorem, which says that if the basic Heegner point x0 over K is not torsion, then the rank, or if you wish, the co-rank of the Selmer group over K is 1. So this is the same kind of a principle. Whenever you have a non-trivial, whenever you have an Euler system with the bottom element which is non-zero, then the Selmer group should be one-dimensional. Okay. So Kolyvagin proves that over K, and then by working over various layers Kn, you can deduce the same result in the limit. Okay. So morally, you should view Iwasawa theory again as some kind of a deformation result, and so this is somehow the generic rank. When I gave you the idea of the proof, then there was a statement that somehow Euler system should give you a result about the generic rank. So this is the result of Bertolini, coupled with Mazur's conjecture. The generic rank in this anti-cyclotomic family is 1. All right. So what we have to do now is to somehow relate, to prove that this generic rank has the same parity as the special rank, right? Namely, somehow the thing which is here. So this means that theorem 2 would follow from the following result. Theorem 3, which is just a purely relative statement which compares the co-rank of the Selmer group over K as a ZP module with the co-rank of S infinity as a lambda module. So this says that under the assumptions of theorem 2, the special co-rank, the co-rank over ZP of the Selmer group over K is congruent to the co-rank over lambda of S infinity modulo 2. So let me denote this number by E. And so now I'm completely ignoring the previous story saying that this is equal to 1. Okay? Now all I want to do is to prove theorem 3 without really specifying this generic rank. This is so E is this generic co-rank. So, proof of theorem 3. Yeah, so what I want to do now is to reduce theorem 3 to theorem 4, surprisingly. But before I state theorem 4, let me give you a few more definitions. So first of all, the ring lambda has the standard involution as any group ring has. So let me denote it by iota. This is the standard involution lambda, which is given by iota of gamma equal to gamma inverse for every little gamma in capital Gamma. Otherwise it is ZP linear. So this is standard involution. And now in all of this business I can ignore finite submodules of various Iwasawa modules. So let me just remind you that the lambda module M is called pseudo-null. In our situation, this just means that it's finite if it has finitely many elements. Now the proper definition in cumulative algebra is that it's finitely generated and the codimension of the support is at least 2, but since lambda is two-dimensional, this amounts to the same thing. So this means, so this is the same thing as saying that M is of finite type and the support of M is just contained, is just the maximal ideal. This is the maximal ideal. Support over lambda. And so it will be useful to ignore those finite modules or pseudo-null modules completely. So I will be working in the category C, which is the quotient category of all the lambda modules, modulo pseudo-null modules. But sometimes there will be also modules of the type lambda over p or lambda over p squared. I can also ignore those, although they won't actually appear, but just in case. So let me go C prime, another quotient slightly. I'm also going to ignore modules which are possibly supported at p. So I divide by those modules which are of finite type and such that the support of M is contained in the set consisting of the maximal ideal and of the ideal generated by P. So the point is that in this category C, finitely generated modules over lambda behave exactly like modules over the Dedekind ring, because I'm just ignoring the unique point of codimension 2. And so this means that this module, well, let me dualize. So if I take the Pontryagin dual of my S infinity, then it has a torsion part. And then torsion-free part, but the torsion-free part in this category is really free. So I have L to E, lambda to E, where E is this generic co-rank. Now let me call this module N, this torsion module. Now of course we have a structure theory of lambda modules up to, in this category C. So again, in C, we know that N is sum of its p primary parts. So you take the sum over all prime ideals of lambda of height 1. So you take the sum over all, and so we have lambda modulo p to the n with some multiplicities, mn, mpn. Almost all exponents are 0. And so if you want, in this category C prime, you have the same, but only for the ideals different from, you ignore the path, the ideal generated by P. All right, so how do we prove theorem 3? As I said, we reduce it to theorem 4, which is the following. It says that in this category C, there exists a non-degenerate pairing of this module N with itself, with values in the quotient ring of the fraction field of lambda modulo lambda, with the following properties. So first of all, the pairing between y and x is minus iota of xy, and the pairing between lambda x and mu y is equal to lambda times iota mu times the pairing between x and y. So here lambda and mu are scalars in lambda, and x and y are some elements of n. In other words, there is a non-degenerate skew-Hermitian form. It is almost like the Castle-State pairing, except that we have lambda here instead of zp, and we have also this involution. All right? So the construction of this pairing will happen in the last 5 minutes of the 4th lecture, I think. It needs some preparation. But let me now prove the implication of theorem 4 implies theorem 3. Okay, non-degenerate in C. And even the map is in C. What?
Formulas.
Well, I think the formulas can all be expressed in terms of some cumulative diagrams. You can embed every category to some category of functions like pre-sheaves, whatever. Yeah? Okay. Okay, so proof of the fact that...
Which might answer, can't you work in lambda tensor QP?
For example, but in fact this is stronger.
I know, but has that answer?
That's correct. In fact, if you just want to prove the parity result, much less structure is enough.
Yeah, I think that answers the question, really.
I don't know.
You don't have to worry.
I think the pairing itself is interesting.
Okay.
Yeah. Okay, so how does it work? In fact, I define it on a slightly different object, where it's really an honest map. And then the formulas hold there, except that my object is not quite this n. It's only isomorphic to n in C, canonically. So it differs from n by some finite thing. Does this answer the question? Okay, so proof of the fact that theorem 4 implies theorem 3. So we really need a otherwise we need something where this involution doesn't appear. But so let me just say that this really works in general in Iwasawa's theory. If you have an ZP to the R extension, then one can do this maybe replacing C by C prime. Okay? But so far I haven't used the fact that in fact I have a dihedral extension. That's what I'm going to do now. So using this tau, I can define another pairing. So define a new pairing with a round bracket, be the old pair between x and y to be the old pairing between x and tau y. And this takes care of the involution, because then this new pairing round bracket is again a pairing on n cross n with values in fraction field of lambda over lambda, again in this category C, but it's now lambda bilinear. Straight. And non-degenerate. In this category C. So it's almost symplectic, apart from a factor of 2, which is harmless for us. And so then, so this means that if you localize at every prime ideal of lambda of height 1, sorry, this is 1, this is lambda. These are not the same. The localization of lambda p is a dvr. And so if you look at the localization of this pairing, so this round bracket is a pairing on np cross np, now with values in the fraction field of lambda p, well, it's the same thing as the fraction field of lambda, divided by lambda p. So this is, as in what I called lemma 0 last time, except for one case, except there's this minor difference between skew-symmetric and alternating. So except if p is equal to 2 and if this curly p is the ideal generated by p. But again, this is harmless. So in those cases, I get from the structure theorem that the localization of NP is really a sum of 2 lambda p modules, apart from this exceptional case. So that's why I stated the elementary lemma 0 last time. And so this means that in this quotient category C prime, which takes care of the possible exceptional case, my module m is my module n is isomorphic to the sum of 2 copies of the same lambda module, because it's true in all the localizations. And remember, and therefore I have this exact sequence 0, m plus m, as infinity dual, and then lambda to the power e. In this category C prime, and therefore now in the category of QP modules, if I take the coinvariance of tensor with QP, I get 0 goes to coinvariance of m twice, tensor with QP, then the coinvariance of S infinity tensor with QP, and here QP to the power e. And this, of course, is the same as the Pontryagin dual of the Selmer group over K tensored with QP by Mazur's control theorem. And now we are done, because then the co-rank of the object in the middle has the same parity as the object on the right, because here I have something twice. Yeah? And yeah, so this is Mazur's control theorem. And so the co-rank of the Selmer group over K is equal to E plus twice the rank of the gamma coinvariance in M, therefore it's congruent to E mod 2. So this means that theorem 3 indeed follows from the existence of this high-dimensional skew-Hermitian pairing in theorem 4. Well, let me make 2 remarks. Well, in fact, I'd like to make 3 remarks, but I don't think I'll have time for all 3 of them. One doesn't actually need any of this duality business if one wants to prove only slightly weaker version of the results. So, remark. So one does not need theorem 4 for the following. Well, not theorem 4, nor Bertolini's result, in fact, for the following. Namely, theorem 1 prime, a weaker version of theorem 1, says that, under the same assumptions, that if the analytic rank of E over Q is odd, then the Selmer group, then the rank of the Selmer group is greater than or equal to 1. So this does not need any duality result. And of course, there's a similar result over K, which says that if the imaginary quadratic field K satisfies the Heegner condition, then the corresponding Selmer rank of E over K is again greater than or equal to 1. So why is this true? Well, this is fairly easy, given what we've seen. So first proof of theorem 2 prime. So by Cornu and Vatsal, well, Cornu twice and Vatsal, we know that the rank over lambda of S infinity dual is greater than or equal to 1. And therefore, this means that the rank over Zp of the Selmer group over K, which is just the rank over Zp of the gamma coinvariance in S infinity hat, is again greater than or equal to 1. Yeah? This is again Mazur's control theorem. Now, the proof of the fact that theorem 2 prime implies theorem 1 prime is exactly the same argument as we had before. Yes? So again, find, there exists K such that, well, satisfying the Heegner condition and such that the analytic rank of the twisted curve ED over Q is 0. Therefore, by Kolyvagin, the Selmer rank of ED over Q is 0. And therefore, we get the result because now the Selmer rank of E over Q. Remember that this additivity formula. This is the Selmer rank of E over K minus the Selmer rank of ED over Q. But the second term is 0, and the first term is at least 1 by theorem 2 prime. So this is at least 1. So for those two weaker statements, there's no need to do any duality business, and there's also no need to redo Bertolini's result. The last remark I want to say that, again, all we really need is to apply Mazur's control theorem. So to construct this whole pairing in theorem 4 is a little bit of an overkill. All one needs is its localization somehow at the kernel of the augmentation ideal. In fact, it's enough to have just its filtration by the J-adic filtration, where J is the kernel of the augmentation ideal, and these objects are more or less known. The first graded quotient is just the p-adic height pairing, and then the next ones are the higher or derived height pairings, which were first constructed with lots of other assumptions by Bertolini and Darmon. So if you are interested just in the proof of the parity result, in other words, in theorem 3, then it's sufficient to construct those pairings without any additional assumptions and prove their basic properties. So I think I'll have time to say more about this at the end of my last lecture. Thank you for today.